Most of us grow up with a comforting picture of light. It takes the shortest route, like a disciplined arrow from point A to point B. A laser looks like proof. A flashlight aimed at a bathroom mirror feels even more convincing. Clean geometry, obedient rules, angle in, angle out. So we assume a photon picks one path and sticks to it. But if light is that single-minded, why does it turn strange the moment you give it a slit, a prism, a diffraction grating, or a thin film on a camera lens? Why do bright and dark bands appear where one straight line should have been enough? Why did scientists argue for so long about whether light is a wave, a particle, or something that won't stay in either box? Tonight, we step into Richard Feynman's answer. Instead of asking which path light takes, he asks us to imagine this. Light explores every possible path, and what we observe is the final sum, where possibilities reinforce or cancel. So here's the question that carries us. How can something as small as a photon try every route? And what does that imply about the reality we call solid? Stay with me, and you'll leave with a simple visual way to feel the path integral, and a calmer, sharper intuition about chance and choice. If we are going to question the way light moves, it is only fair to begin in the place where our certainty about it was born. Inside a small room, with sunlight on the wall, and a mind that still believes the world is simple. For most of our lives, when we picture light, we do not picture an ocean or a fog. We picture a stroke, a clean line, drawn from a lamp to a table, from the sun to the earth, from a screen to the pupil. In our school notebooks, the path of light is always a straight arrow, obedient and thin, like a disciplined soldier walking the shortest route between 2 points. We sketch it almost without thinking, because it feels obvious that this is how the world behaves when no one is watching. Imagine a child alone in a bedroom on a late afternoon, when the sun is low and the air is full of golden dust. A narrow beam sneaks in through a gap in the curtains and lands on the wall. The child finds an old hand mirror, a little scratched, and does what children have always done: tilts the mirror and watches the bright patch of light jump from wall to ceiling to closet door. With each small rotation of the wrist, that patch moves as if a rigid, invisible ruler were being swung around the room, pivoting about the mirror, connecting the sun outside to whatever surface it chooses to touch. Nothing in that scene looks mysterious. The child learns, long before there is any equation, that if you tilt the mirror a little this way, the spot climbs. Tilt it the other way, it falls. Later, in a textbook, this domestic magic is translated into a clean sentence. The angle at which the light arrives is equal to the angle at which it leaves. A triangle is drawn, a few Greek letters are added as decorations, and suddenly the living experience of a bright patch on a dusty wall has been flattened into geometry. This rule feels reassuring. It tells us that the path of light is not only straight, but also unique. From the sun to the glass, from the glass to the wall, there is one line that matters, and the line is so well behaved that you can calculate it with a protractor. You can almost hear the world promising you. If you know the position of the source and the angle of the mirror, you know everything you need to know. There are no hidden alternatives. Cinema has taught us the same lesson, only more beautifully. Think of that early scene in the film, set around a failing farm and a hidden NASA project, when the sun pours into Cooper's wooden house at a slant. The light cuts through the dim air in pale golden sheets, every dust grain suspended in its own tiny orbit. The beams look like they have been drawn in with a ruler, crossing the room in straight columns, honest and stable. It is a comforting image, light as a gentle architecture that never surprises us, silently filling the spaces we build. Even the way we talk about light obeys this picture. We say that light travels from here to there, as if it were a little bullet sprinting across empty space. We talk about light rays hitting a surface, bouncing off like elastic balls, passing through glass as if it were water. The verbs all belong to a world of objects with clear trajectories. Nothing in our everyday language, suggests that light might be doing something more than simply threading a single line through space and time. By the time we reach secondary school, that picture has become a kind of mental operating system. We draw rays going straight through lenses, bending a little at each surface, converging neatly at a focus. We learn how to design a magnifying glass on paper, how to show a beam entering a block of glass and leaving on the other side, shifted but still perfectly straight. The law that the angle of arrival equals the angle of departure, and the companion rules for refraction feel like they describe the one geometry that light is allowed to trace. The world, in this version, is a calm stage with clear lines painted on the floor, and light is an actor who never misses its mark. For a long time, this was enough. Engineers built telescopes that collected starlight and focused it onto eyepieces. They built microscopes that pulled hidden worlds of cells and crystals into view. They shaped glass into camera lenses, projector lenses, spectacle lenses, all on the assumption that light is a faithful, almost boring, walker of straight paths. If you know how it enters and what it passes through, you know where it will end up. And for much of the 19th century, that assumption seemed to be rewarded, over and over, with success. Even the great early experiments that revealed the spectrum of colors inside white light did not yet threaten this comfort. When a certain English physicist in the 17th century let a narrow shaft of sunlight pass through a small glass prism and watched it spread into a fan of reds, greens, and blues on the wall, he confirmed that light could be decomposed into different colors, each bent by the glass to a slightly different degree. But the underlying picture still held. Each color was imagined as its own set of straight rays, each ray taking one definite path through the prism. The world had become richer, more colorful, but not more ambiguous. This is the version of light most of us carry with us into adulthood. A straight line that can be bent, but never confused. A traveler that may slow down in glass or water, but never seems uncertain about where it has been or where it is going. And as long as we only look at mirrors and lenses, this version behaves well enough to survive. The trouble begins when the world refuses to stay within the illustrations of a textbook. Take that same light and let it pass through a single small hole in a screen. And on the wall behind you, see not just a crisp circular spot, but a pattern with softer edges, fringes that hint at something more fluid. Now carve two narrow slits side by side. Let the same light pass through, and on the detector you start to see alternating bands of bright and dark, as if brightness itself were rising and falling like ripples on a pond. Suddenly, the idea of one clean line from source to screen no longer feels like an explanation. It feels like a guess that has been caught out. There is a quiet shock hidden there. If light were truly just a swarm of tiny bullets, each picking one slit or the other, why would there be places on the screen where almost no bullets ever arrive, even though both slits are open? Why would the presence or absence of a path that a particular photon never seemed to take still affect the pattern it draws on the wall? The straight line story begins to fray at the edges, and for the first time, the simplicity that once comforted us starts to feel suspicious. Yet in laboratories and workshops throughout the 19th century, people kept designing and polishing instruments as if the old picture were fundamentally correct. Opticians calculated the curves of glass surfaces, corrected for aberrations, increased sharpness, all by refining the way straight rays were bent and focused. Astronomers turned those laws into giant mirrors aimed at the sky. Surgeons put their trust in precisely shaped lenses that guided light into the human eye. The fact that light behaved like a wave in some experiments could be tucked away into another chapter, another mental folder, without fully rewriting the story. Our intuition, by then, had become something like a well-edited film. All the messy frames, all the moments of blur and jitter had been cut out, leaving only the clean shots, the neat reflection on the bathroom mirror, the sharp glint on a piece of metal, the slender beam from a flashlight piercing the dark. We watched that film so many times that we started to mistake it for the raw footage of reality itself. But what if the cutting room floor is where the real physics lives? What if the apparent simplicity of a single straight path is not the fundamental rule, but the end result of something far more tangled and indifferent to our preference for clarity? The distance between a light source and your eye looks so modest on a drawing, one line between two dots. The truth, as modern experiments keep whispering, seems closer to this. Between those 2 points lies an uncountable family of ways light could get from one to the other. Ways that skim, ways that detour, ways that loop uselessly and cancel each other out. Our straight ray is not the only story. It might not even be the main one. It could be just the surviving trace of an argument among possibilities that we never see. If that is so, then the simple scene of a child playing with a beam in a bedroom is already hiding something unsettling. From the sun, to the mirror, to the wall, to the child's retina, there may be a vast, invisible democracy of paths, most of which never get to vote in the final image. What reaches the eye is only the outcome of their interference, the ghost of a calculation that nature performs without asking us. The question then is not just whether our straight line is a little inaccurate. The question is whether it is the wrong kind of picture altogether. If our deepest intuitions about the path of light are merely approximations, polished by centuries of limited experience, then what is really unfolding in that space between a glowing filament and the back of your eye? Somewhere in the middle of the 20th century, a physicist with a restless mind and very little patience for comforting stories decided to treat our usual intuition as exactly that, a summary, not a law. He proposed that instead of asking which path light takes, we should dare to imagine that it, in some sense, explores them all, and that what we see is the result of an immense, silent summation. In the chapters ahead, we will follow him into that full version of the story, where light is no longer the obedient thin line we grew up with, and the empty space between 2 points turns out to be crowded. The idea that the empty space between 2 points might be crowded already sounds strange, and it only becomes stranger when you realize how many times we have tried to clean that crowd away with a new story, a new picture of what light is supposed to be. Every few generations, humanity seems to fall in love with one of those pictures. We build instruments, philosophies, even the way we talk about truth, on top of it. And then light quietly produces a result that does not fit, and the whole structure shudders. Imagine the 17th and 18th centuries as a long corridor lit by candles and oil lamps. In that glow, one figure dominates the hallway. Isaac Newton. He thinks about light the way he thinks about planets and falling apples, as something made of pieces that move. In his mind, a beam of light is a stream of tiny projectiles, corpuscles, fired from a source and flying in straight lines until they hit something. The beauty of this view is that it fits perfectly with the straight path intuition. Each little corpuscle is like a miniature bullet. It leaves the sun, or a candle flame, or the polished face of a mirror, and travels along a single track. When it meets glass, reflection or refraction are just different outcomes of the same basic game. A particle comes in, interacts with the surface, and exits along a definite route. No smearing, no rippling, no ambiguity. Newton's authority was immense. When he said that light was made of particles, most of Europe nodded. For much of the 18th century, the corpuscle picture was not just a theory. It was almost a default setting of the educated mind. If someone had suggested that a ray of light might somehow be taking more than one path at once, the idea would have sounded less like physics and more like superstition. And yet, almost in parallel, there was another mind drawing a very different picture. Christian Huygens, working in the same broad period, dared to imagine light not as a stream of tiny stones, but as something that spreads. In his view, every point that light reaches becomes, in turn, a source of ripples, like a drop falling on a still pond. From each point, a little expanding wavefront moves outward, and the pattern we see is the envelope of all those overlapped circles. This wave picture could also explain reflection and refraction, even the way light bends as it goes from air into glass. Mathematically, it was elegant. Visually, it felt softer, more fluid, less aligned with the straight arrow that our eyes and our instincts keep insisting on. For a long time, Huygens's version lived in the shadow of Newton's prestige. It is not that people never read him. It is that when a particle picture and a wave picture both seem to work, and the most famous physicist in the world supports the particles, the choice does not feel like a choice. The wave view was there, like a book on a shelf that very few people reached for. Then came a quiet disruption. On a November day in the early 19th century, a physician and polymath named Thomas Young stood before the Royal Society in London and gave what was known as the Bakerian Lecture. The date was the 24th of November in the year 1803. The subject was, simply, light. But the way he chose to ask about it was not simple at all. Young described an experiment that sounds innocent until you really look at its implications. Let a beam of light pass through two narrow slits cut close together in an opaque screen. On a second screen behind them, you do not get two bright stripes as you might expect from the particle picture. Instead, you see many thin bands, bright and dark alternating, like the pattern on a finely combed shell or the ripples where two sets of water waves meet. If light were truly just made of flying pellets, each pellet going through exactly one slit, those dark bands would be a mystery. How does a place on the screen become a zone that almost no pellets ever choose to visit, even though there is a clear line of sight from the source through at least one slit to that point? The wave picture, on the other hand, embraces this immediately. Peaks from one slit meet valleys from the other, and they cancel, leaving darkness. Standing in that room, listening to Young, you would have felt something subtle give way inside that old straight-line certainty. He was not simply saying that light sometimes behaves like waves. He was saying that if you want to understand those delicate bright and dark fringes, you must allow that what leaves the source is capable of dividing, spreading, overlapping with itself, and producing regions of both reinforcement and cancellation. The idea that light takes one path or the other starts to look less like a law and more like an assumption. Many of Young's contemporaries did not welcome this with open arms. Some doubted his measurements. Others questioned the sharpness of the slits, the stability of the light source, anything that might rescue the more comfortable particle picture. But the evidence did not go away. Other experimenters repeated and refined his work. Slowly, the mental weight shifted. Light might still have a particulate side, people thought, but it was becoming harder to deny that it also carried a wave character. In the 19th century, this wave side was taken up and developed with mathematical ferocity. Augustin Fresnel and others extended the wave theory to explain diffraction, polarization, and a host of subtle optical phenomena. The more they pushed, the more the wave picture seemed to offer a coherent language for what light does. And then James Clerk Maxwell came along and raised the stakes even further. Maxwell did not start with light. He started with electricity and magnetism, with the way charges attract and repel, the way magnets pull and twist, and the way changing electric and magnetic fields seem to summon each other into existence. He wrote down a set of equations that unified this zoo of electrical and magnetic effects into a single framework. When he looked inside those equations, he found something remarkable. They predicted waves. These waves were not waves in water or air. They were waves in the electromagnetic field itself, self-sustaining oscillations of electric and magnetic components that propagate through space. Maxwell calculated the speed at which these waves should move. That speed matched, within the accuracy of the measurements of his time, the known speed of light. It was a simple comparison with enormous consequences. The conclusion was inescapable. Light is an electromagnetic wave. The light from a candle, from the sun, from distant stars, is nothing more or less than this particular form of field oscillation moving through space. For a while, it felt like the story could end there. Light had been given a new identity, deeper than corpuscles, more mathematical than Huygens's ripples. Rays were now understood as convenient arrows drawn along the directions of electromagnetic wave propagation. The straight-line picture became a kind of shadow of a richer theory, still useful for designing lenses and mirrors, but no longer pretending to be the whole truth. If we stopped the narrative at this 19th century moment, we would have a clean arc. Humanity starts with particles, moves to waves, unifies waves with electromagnetism, and closes the book. But the universe did not cooperate with this neat chronology. As the 19th century gave way to the 20th, a new set of observations began to cause trouble. One of them was the way hot objects glow. When you heat a piece of metal, it first glows red, then orange, then white. The exact way the brightness and color depend on temperature refused to match the predictions of classical wave theories. Another, perhaps more violent, conflict came from what happens when light hits certain metals and ejects electrons from them. A process that came to be called the photoelectric effect. Classical wave thinking said, the energy of a wave is spread out, and the more intense the beam, the more energy should be delivered to the metal surface. If you shine enough light, even if it is low frequency, you should eventually kick some electrons free. But experiments showed something else. Below a certain frequency of light, no electrons were emitted, no matter how intense the beam or how long it was applied. Above that threshold frequency, electrons came out promptly, and increasing the intensity of the light increased the number of electrons, but not their individual energies. It was as if the energy was arriving in localized chunks, tied not to the beam as a whole, but to its color. In the year 1905, a young patent clerk in Bern, Albert Einstein, proposed a radical interpretation. Building on Max Planck's earlier work on blackbody radiation, he suggested that light is quantized. That is, the electromagnetic field does not exchange energy with matter in a continuous way, but in discrete packets. Each packet, later called a photon, carries an energy proportional to the frequency of the light. In this view, the photoelectric effect becomes simple. If each photon carries too little energy to free an electron, no amount of piling up such photons will help. Once the photon energy exceeds the binding energy of the electrons, each photon that hits the right way can kick one electron out. The threshold frequency is just the point where the photon energy crosses that binding barrier. The weird behavior of glowing objects also becomes tractable. The distribution of energies in the electromagnetic field must follow a certain statistical rule, and that rule naturally emerges when you treat the field as made of quanta. But this cure came with a new disease. After Maxwell, we had learned to think of light as waves. After Einstein, we were being told that it also behaves as if it were a shower of particles, but not the old Newtonian corpuscles. These are quanta, indivisible, with both wave and particle characteristics. In some experiments, light interferes with itself like a wave. In others, it strikes detectors as crisp, localized events. The straight-line intuition that survived into the 19th century was now wounded in a different way. It was not only that light refused to commit to being a wave or a particle, it was that any picture you tried to draw in your head, using familiar objects like bullets or ripples, failed somewhere. If you insisted that light must always go through exactly one slit, the interference fringes mocked you. If you insisted that it must be a smooth wave spread everywhere, the graininess of detections contradicted you. Nature was giving accurate, reproducible answers, and our metaphors were failing the exam. At this point, it is tempting to turn the story into a tug-of-war. First particles win, then waves win, then quanta arrive and declare that both sides are right and wrong at once. It sounds dramatic, but it misses something important. The real violence here is not between schools of thought. It is in the way light continually forces us to abandon the comfort of single-category thinking. From Newton's corpuscles to Huygens's ripples, from Young's lecture in London to Maxwell's equations, from Planck's energy elements to Einstein's photons, each new attempt to pin light down has carried with it a silent hope that this time the picture will be final. This time, we will have reduced the complexity of all those experiments to one simple, stable mental image. Light has not cooperated with that hope. It has rewarded us with predictive power, with technologies that reshape civilization, with equations whose accuracy is almost frightening. But whenever we have tried to turn one of our images into a definition, it has slipped away. Richard Feynman grew up in the aftermath of this whole sequence. For him, the fact that light could act like both a field and a particle was not a crisis to be resolved by choosing one side. It was a fact to be absorbed and then re-expressed in a new language altogether. Instead of asking, again, what light really is. He asked a different kind of question. Given all these experiments, given this dual character, what must light have been doing along every possible way from source to detector to produce the patterns we see? It is a shift in emphasis that looks small in words, but it cuts deep. The focus moves from the identity of light to its histories, from the label on the entity to the sum over its paths. And once you accept that, the straight line does not disappear, but it is demoted. It becomes one visible trace emerging from a crowd of invisible alternatives, the calm signature written on the surface of a process that is anything but calm underneath. That is where we are heading next. Not into yet another debate about whether light is this or that, but into a way of thinking where the question itself loosens, and the emphasis falls instead on what light does when we allow it to consider every road, not just the one our eyes prefer. To feel how far our old pictures of light can stretch before they tear, it is enough to stand in front of one experiment, in a quiet room, and let a very simple pattern slowly draw itself in front of your eyes. Imagine the scene. The room is dark, the kind of thick darkness where the edges of furniture dissolve. At the far end, there is a small wall or a screen. Somewhere behind you, a very modest light source has been tamed and narrowed so that it gives off a thin beam, like a blade. Between the source and the screen, there is a barrier, with two narrow slits cut side by side. That is the entire stage. Nothing rotates, nothing explodes. It is a setup that you could sketch in a few strokes on a napkin. If you think like a person raised on straight lines and bullets, your expectations are simple. Light leaves the source, travels forward, and when it meets the barrier, it has a choice. Go through the left slit or the right slit. Through each slit, a fan of rays spreads out and hits the screen. Two slits, two fans, two regions of brightness. Perhaps they overlap in the middle and make a slightly brighter strip, but the basic picture is two glowing patches where the rays land. Now imagine that someone switches the apparatus on and the screen begins to glow. You look closely. The darkness is not simply cut by two smooth columns of light. Instead, you begin to see something more delicate, a pattern of alternating bright and dim bands arranged across the far wall, like the lines in a finely woven fabric. Where you expected a simple overlapping of two beams, you find a series of fringes, bright, dark, marching across the field of view. If you have ever watched waves from two stones interfere on the surface of a pond, the sight is familiar. Where the crests from one stone meet crests from the other, the water rises higher. Where crests from one meet troughs from the other, the water calms. Bright and dark in the light pattern are playing the same game. When the contributions from the two slits arrive in phase, the intensity is strong. When they arrive out of phase, they cancel and leave darkness. Already, the straight-line picture of light has taken a hit. This is not the behavior of tiny pellets, each choosing one slit. This is the behavior of something that can, in some sense, pass through both openings at once and interfere with itself. The two fans of possibility coming from the slits do not simply add. They add and subtract depending on where they meet. Now change the way you imagine the source. Instead of letting it send a steady flood of light through the slits, we dim it and dim it again, until it is so weak that, by all our best estimates, at most one photon is in flight at a time between source and screen. The room is still dark. On the screen, nothing visible is drawn yet, but if your eyes were sensitive enough, you would see occasional flashes, a single grain of brightness appearing here, another there. Each arrival is a discrete event, as if a tiny stone of light had struck and left its mark. You watch the screen over time. At first, the bright specks look scattered in a way that feels random. There is no visible order. But as more and more photons arrive, each leaving its own little dot, the pattern begins to emerge. The scatter of points starts to thicken in some regions and thin out in others. Slowly, the familiar interference fringes appear, not as continuous bands painted all at once, but as the statistical shape traced by many single impacts. What is unnerving here is that at no point were two photons in the apparatus together to talk to each other about how to arrange this drawing. Yet they have produced a pattern that requires, in our old language, a wave interfering with itself. It is as if each photon, somehow, in some way that does not fit into the usual categories, has behaved as if it had access to both slits at once. As if it had taken more than one path. You might try to rescue the straight-line intuition by inventing an invisible conversation. Maybe each photon leaves a faint trace, or changes the apparatus in some subtle way that influences the next one. But physicists are stubborn. They are very good at making sure that the source sends the photons so sparsely that there is no overlapping in time, and that the apparatus has time to relax between arrivals. The pattern persists. It is not an echo of one photon talking to another. It is a single photon, again and again, acting as if all routes are in play until the moment it hits the screen. For a long time, this sort of thought experiment was done with light alone. Then, in the early and middle decades of the 20th century, people started passing other things through the slits. First electrons, accelerated and focused, sent through two narrow openings and onto a detector. The result was the same essential story. When you do not ask which slit the electrons go through, the arrival pattern over time forms an interference fringe. Each electron hits at a definite point, but the statistics of many hits carve out a wave-like image. Later, as technology advanced, similar experiments were run with neutrons, with atoms, even with large molecules, each one a complicated cluster of nuclei and electrons. The size of the objects increased, but the message did not change. As long as you set up the apparatus so that, for all practical purposes, the system cannot leak information about which slit each particle used, you get interference. Take that possibility of information away, and the interference collapses, replaced by two bland clumps, one behind each slit, exactly as the straight-line picture would predict. The two-slit experiment, in all its variations, has become a kind of mirror in which our intuitions go to burn. Every time we think we have built a mental model that can handle it, the details defeat us. The natural human reaction to confusion is to try to look more closely. If the pattern on the back wall is so strange, perhaps we can put tiny detectors right at the slits and watch which one each particle uses. It feels like installing a set of cameras at the doors of a hallway. You imagine seeing a photon or an electron go left or right, and then checking where its dot appears on the detector. Surely, if we can track which opening it uses, the mystery will soften. So we try. We modify the experiment so that each slit is monitored. In practice, this might mean adding a device that interacts differently, depending on whether a particle passes through one opening or the other, leaving a mark in the apparatus that, in principle, we could later read. The key point is this: the setup is now capable, even if we choose not to look, of telling us which path each particle took. And then something almost spiteful happens. The interference fringes vanish. Instead of delicate bright and dark bands, the accumulated impacts on the far screen arrange themselves into a straightforward sum of two single-slit patterns. In other words, they form two overlapping blobs, brighter in the middle, fading toward the edges, but without any fine alternating structure. It is exactly the picture you would get if you assumed that each particle went through one slit or the other, and that their contributions simply added like sand piles. The very act of making which path information in principle available, even without any human actually looking at it, has changed the outcome. The universe, in some quiet and stubborn way, seems unwilling to give us both stories at once. We can have a world in which particles behave in ways that produce interference, but then we must give up the right to say which route each one took. Or we can have a world in which we tag each route, but then we must live with the bland, non-interfering patterns of classical expectation. It is tempting here to anthropomorphize, to imagine nature as a shy performer who shuts down the magic whenever the audience gets too close. The truth is less playful and more severe. What the experiment is really telling us is that our categories of particle path and interference pattern are mutually exclusive when applied to the same run of events. The mathematics of quantum theory predicts this trade-off precisely. long before anyone builds the apparatus to check. Reality, when tested, sides with the mathematics. In the later decades of the 20th century, this tension was pushed into an even more disturbing corner by an idea John Wheeler liked to call the delayed choice experiment. The core thought is simple and unforgiving. Instead of deciding in advance either to let the particle go through the two slits unobserved or to measure which path it takes, what if we delay that decision? What if we set up the apparatus so that the choice to preserve or erase which path information is made only after the particle has already entered the region where the paths differ? In one version of this, you can replace the slits with different optical elements, but the spirit is the same. A single photon leaves a source, encounters a device that offers it two distinct routes, and then, farther downstream, there is another arrangement of mirrors and detectors that can be configured in two ways. In one configuration, the routes are recombined in such a way that interference is possible. In the other, the routes are separated so that detectors can, in principle, tell which path the photon took. Wheeler's question was, if we wait until the photon is already in flight, until it has passed the first element, and only then choose which configuration to use at the end, what do we see? Quantum theory, as encoded in its equations, calmly predicts that the statistics of detections will match whichever configuration is actually present at the end, no matter when we made the choice. When experimentalists began to implement versions of this scheme, starting in the last quarter of the 20th century and refining them over the years, that is exactly what they observed. If the final apparatus is set to recombine routes and allow interference, the pattern of many photons builds up with fringes, as if each photon had gone through both paths. If the final apparatus is set to reveal which path information, the pattern is that of two non-interfering beams, as if each photon had only ever gone through one. The unsettling part is not that the outcome depends on the setup. That is normal. It is that, in these delayed choice scenarios, the photon is already well on its way before the final configuration is fixed, and yet the total observed behavior is consistent with a world in which the photon knew from the beginning, whether it was in an interference-friendly universe or a which path revealing one. If you try to tell the story with a classical picture of a little object choosing its route at a definite time, you quickly tie yourself into knots. You either have to allow backwards in time influences or abandon the idea that the photon ever had a definite path in the first place. Physicists are generally not fond of spooky stories about signals going backward in time. The more sober response is to question the assumption that there is a single actual path that the photon took, waiting to be discovered. The two slit and delayed choice experiments seem to conspire to pry that assumption out of our hands. They suggest that insisting on one concrete trajectory for each quantum particle, independent of how we choose to arrange the rest of the apparatus, is simply not compatible with what we see when we look. When you take all of this in, there is a particular kind of discomfort that sets in. It is not the thrill of mystery packaged for entertainment. It is quieter, heavier. You realize that the mental move you have made since childhood, drawing one line between 2 points and calling that what happened, may not be available to you at the fundamental level anymore. Between light source and screen, between electron gun and detector, between even two states of an atom, the idea of a single thin history threading through space-time starts to look like a story we tell ourselves because it feels humane, not because the world demands it. At this stage, it is natural to feel a sort of intellectual helplessness. All the familiar ways of explaining things break down. If we cling to particles talking tiny straight walks, we cannot make sense of the interference. If we cling to waves smeared everywhere, we cannot make sense of the sharp impacts and the way a simple detector can erase fringes. We stand in front of the two-slit pattern like someone staring at a movie whose plot twists have been rearranged, sensing that there is a script, but not being allowed to see it. This is the place where many interpretations of quantum mechanics begin to proliferate. Some say that the particle takes all paths in many parallel branches of reality, and interference is a bookkeeping effect across these branches. Others say that the wave function is a field of possibilities that collapses when an interaction happens, and it is meaningless to talk about paths before that. Still others try to smuggle in hidden variables, assigning definite but inaccessible properties to each particle, only to find that certain experiments involving correlations between separated particles rule out the simplest versions of such schemes. Amid this forest of ideas, the raw facts of the two-slit experiment remain solid. Whatever story we tell, it must at least reproduce those facts. A particle sent one by one toward two openings produces an interference pattern if no which path information is available. The same particle, in the same setup, produces a simple sum of two distributions if the apparatus is capable of revealing the path. Delayed choices about how we configure the end of the journey still feed back into which global description can be consistently assigned, without any sign that the particle ever carried a little flag proclaiming, "I went left," or "I went right." It is here, on this scorched ground, where classical intuition has been tested and found wanting, that Feynman chooses to plant a different kind of flag. Instead of laboring to rescue the question, which slit did the particle really go through, he suggests that we set that question aside as ill-posed. Rather than fighting to keep the concept of a single path, he proposes that we embrace, mathematically, the idea that every possible path from source to detector plays a role. In the language he developed, each path carries with it a complex number, an amplitude, that can be drawn as an arrow in a plane. The length and angle of this arrow depend on a quantity called the action, which is itself an integral over the path. To find the total amplitude for a particle to go from point A to point B, you sum the contributions from all paths. Where the arrows point in similar directions, they add and give a large resultant. Where they point in many different directions, they tend to cancel, leaving a small or vanishing total. In that view, the two-slit interference pattern is no longer a paradox. It is exactly what you expect when contributions from paths passing through both openings are allowed to exist and combine. The delicate bright and dark fringes are simply regions where the arrows line up or oppose each other. When you introduce which path detectors, you are, in effect, changing the set of paths that contribute coherently. The arrows no longer all relate in phase in the same way, and the pattern becomes the broader sum of two single slit distributions. We are not yet ready to dive into all those arrows and actions. But we can already see the shape of the answer he is pointing toward. If the attempt to force nature into the mold of this path or that path breaks down under the pressure of the two-slit experiment, perhaps the way forward is not to choose between particle and wave, or between left and right, but to accept that the fundamental description must be about a superposition of everything that could happen. The cost of that acceptance is the loss of a certain kind of comfort. The gain is a language in which the experiments stop looking perverse and start looking inevitable. The question that hangs in the air, then, is this. If we are not allowed to ask which path a photon took, what are we allowed to ask? How do we talk about what has happened between source and screen without smuggling back in the very intuitions the data have just burned down? Feynman's response, characteristically, is not to offer a philosophical slogan, but a rule for calculation. Stop arguing about which route the particle really chose. Instead, write down all the routes, assign them amplitudes, and add. Out of that sum, he promises, will emerge the patterns we see on our screens, the reflections in our mirrors, and the ordinary straight rays of schoolbook optics as a kind of mirage, a macroscopic echo of an underlying democracy of paths that never shows itself directly. If we stop asking which route a particle really took, we are not left in a void. We are left with a strange kind of freedom, to build a new picture from the ground up, one that does not owe anything to the straight lines we drew as children. Richard Feynman spent most of his life living in that freedom. He had very little patience for fancy words that covered over confusion. Ornate philosophical talk about waves and particles made him restless. What he wanted was a way of thinking that did two things at once. It had to be loyal to the mathematics, because the equations were the only part of the story that consistently passed every experimental test. And it had to be simple enough that, in principle, you could stand in front of a blackboard and show a first-year student how to use it. For him, this was not a contradiction. If a theory really described the world, then there ought to be a way to strip it of its decorative clothing, and show its bones without losing its power. That stubborn belief is what led him to one of the most unsettling and beautiful ideas in modern physics: the path integral view. In that view, when you ask for the probability that a photon travels from a source to a detector, you are not supposed to imagine it tracing one line between the two. Instead, you are asked to imagine something far more extravagant. You consider every possible path that connects the starting point and the ending point. Not just the obvious straight one, not just a couple of nearly straight ones, all of them. Paths that dart up and down, paths that loop back and forth, paths that seem wasteful and absurd. In principle, you include every continuous curve that could be drawn between those points in space and time. At first, this sounds less like physics and more like a kind of madness. How can it make sense to talk as if a single photon, a single quantum of light, has to do something along every imaginable route? How can the world afford that kind of extravagance without collapsing under its own complexity? Feynman's answer was simple, and it did not rely on metaphors of splitting or copying. He was not saying that a physical object literally divides itself into countless temporary clones that roam the universe and then merge. He was saying that the correct way to calculate the probability amplitude for a process is to associate a mathematical contribution with each possible path, and then to add those contributions. The photon that finally hits your detector does not carry a memory tag that says which path was real. What is real, in this view, is the total result of the sum. To make this less abstract, he invented a picture that you can carry in your head. In his public lectures on quantum electrodynamics, including the Sir Douglas Robb lectures he gave at the University of Auckland in the late 1970s, he told the audience to forget about advanced calculus for a while and think about arrows. Each possible way for light to go from point A to point B, he said, can be represented by a little arrow drawn on a piece of paper. The arrow has a direction and a length. The direction, the angle at which the arrow points, is determined by something called the action associated with that path. The length is related to how strongly that path contributes. You can imagine that arrow as the hand of a tiny clock attached to the path. As the photon moves along, the hand turns. The amount it turns depends on the details of the journey: how long it takes, how the energy behaves, how the field interacts with matter. When the photon arrives at the detector, you look at where the clock hand points. That direction encodes what physicists call the phase. Now you do not stop at one arrow. You draw one arrow for every conceivable path, a forest of tiny clocks, each frozen at its final angle. The rule, Feynman says, is that to find the total amplitude for the photon to be observed at B, you must add all those arrows tip to tail. Place the tail of the second arrow at the tip of the first, the tail of the third at the tip of the second, and so on, walking around the complex plane in a kind of drunken vector walk. When you have added them all, you look at the single arrow from the starting point of your walk to its final endpoint. That resultant arrow is what matters. The probability that the photon goes from A to B is given, roughly speaking, by the square of the length of that resultant arrow. Directions that line up build each other up. Directions that oppose each other cancel. At first glance, this seems like a needlessly complicated way to recover something as simple as a straight ray of light. But here is the crucial part. For the vast majority of wildly wiggly paths, the little clock hands end up pointing in almost random directions by the time they reach B. When you add a huge number of arrows pointing almost everywhere, they tend to cancel one another. The walk takes you a little this way, a little that way, and in the end, you do not get very far from the origin. Their contributions nearly vanish. There is, however, a special family of paths for which the clock hands do not scramble so badly. These are the paths for which a small change in the route does not change the action very much. Along those paths, neighboring variations have almost the same phase. Their arrows end up pointing in similar directions. When you add them, they reinforce each other, producing a long, clear arrow. What we call the classical path, the one that a ray of light appears to follow in ordinary optics, is not chosen by the photon thinking. or by some hidden intelligence shortlisting routes. It is simply the path around which the action is stationary, neither increasing nor decreasing sharply when the path is varied. In the language of older physics, this is the content of the principle of least action. In Feynman's reformulation, it becomes the place where the tiny arrows line up instead of cancelling. The result is deeply paradoxical and deeply satisfying at the same time. The straight line that we draw on the board is no longer an assumption. It is an emergent compromise, a chord that rings loud because the surrounding notes agree with it. All the bizarre, looping, implausible paths are still in the calculation. They have not been forbidden. They just happen, in the sum, to mostly silence one another. This way of thinking allowed Feynman to gather all the strange quantum behaviors into one compact formalism. Instead of treating reflection, refraction, scattering, absorption, emission, and interference as separate cases requiring separate stories, he could treat them all as different ways of adding arrows. In his book on quantum electrodynamics for the general public, he walks through examples that look, at first, like ordinary ray tracing problems from school. How does light reflect from a mirror? How does it travel through glass? How do you compute the chance that a photon scattered from an electron ends up being detected in a certain direction? In each case, he draws a few blobs and lines, labels them with arrows, and applies the same rule. Multiply amplitudes along successive stages, add amplitudes for alternative histories, and only at the end take the square of the length to get a probability. Behind these doodles on the board lies a formidable mathematical structure. The action is not just a poetic word, it is a definite functional of the path, defined by integrating a quantity called the Lagrangian along the route. The way those complex phases combine is dictated by the core structure of quantum theory. But for Feynman, the hard mathematics and the simple arrow game were two sides of the same coin. He used the game to give intuition and the mathematics to make precise predictions. The physics community did not treat this as a mere toy. The path integral formulation became one of the pillars of quantum field theory, particularly of quantum electrodynamics, the theory that describes how light and charged particles interact. For the work of constructing this theory, Feynman shared the Nobel Prize in Physics in the mid-1960s, alongside Julian Schwinger and Shinichiro Tominaga. Their approaches looked different on the surface, but at their core, they were telling the same story about how fields and particles exchange quanta. One of the startling outcomes of quantum electrodynamics is how absurdly accurate it is. When you use its rules, including the path integrals, to calculate certain properties of the electron, such as its magnetic moment, and then measure those properties in the laboratory, the numbers agree to many decimal places. That kind of agreement is not an accident. It is a sign that, however strange the language of arrows and actions may sound to us, it is tracking something very real about how the world behaves. It is worth pausing for a moment and connecting this back to ordinary experience. When you sit at home and decide to walk to a cafe a few blocks away, your rational mind tells a simple story. You chose that cafe because you like it. You take, more or less, the shortest route, but if someone secretly filmed your feet and then slowed the footage down, they would see that between the decision and the arrival, there is a whole field of micro possibilities. Slight shifts to avoid cracks, tiny sidesteps to let someone pass, small hesitations at crossings, little detours around parked bicycles or puddles. Each step is a kind of local adjustment, an exploration within a narrow cone of options. You do not consciously evaluate every possible microscopic route through the city. Your nervous system and your muscles handle most of the details without reporting them upstairs. Yet the final path you actually walked is the outcome of all those small negotiations between body, environment, and intention. The path integral view is not saying that a photon thinks or chooses in anything like that way, but it does say that what we call the straight ray is not the primitive fact. It is the survivor of a vast set of possible ways in which the process could have unfolded, weighted and combined by the structure of the theory. The photon does not exploit a pre-existing shortest path. The concept of shortest only appears after you have done the sum and seen which family of routes contribute coherently. This is why Feynman could talk about light trying every path without implying that the world is full of ghost photons. The trying happens in the algebra, not in a hidden physical movie we could watch if only our cameras were better. When we say that a photon contributes along a path, we mean that the amplitude associated with that path is part of the sum that produces the observed statistics. If we change the apparatus so that certain paths become impossible or acquire wildly different phases, the sum changes. The pattern on the screen changes. That is all. Some people find this unsatisfying because it seems to retreat into mathematics as an ultimate refuge. But in physics, mathematics is not a retreat. It is the most honest way we have of stating what follows from what. When Feynman tells you that the path integral accounts for every experiment on light and matter that has ever been performed, he is not asking you to trade intuition for abstraction. He is inviting you to let your intuition grow in the direction of the abstraction. In time, if you stay with the picture, the strangeness begins to soften. The idea that light has one correct path, and that our job is to discover it, starts to feel like a habit, not like a necessity. The idea that there is a whole landscape of possible routes, and that their contributions can interfere, begins to feel natural. You start to see the world less as a sequence of cleanly chosen threads, and more as a tapestry woven from countless potential threads, most of which cancel one another out before they ever become visible. This shift in perspective has consequences beyond optics. In the path integral language, what we think of as a particle moving is replaced by the notion of a history, a line in space-time. Instead of assigning a trajectory and then worrying about how it was chosen, we sum over histories and let the weightings, determined by the action, decide which features of those histories will be manifest in the outcomes. When this framework is extended to fields, not just point particles, it becomes the standard way of doing calculations in high-energy physics. Creation and annihilation, scattering and binding, all become questions of which field configurations contribute significantly to the path integral. Yet Feynman never lost sight of the human scale of the idea. In his Auckland lectures and in his later writings, he kept returning to the arrow picture, the little spinning clock hands, because he knew that, without some visual anchor, the whole thing could drift away into formalism. He did not want students or lay readers to memorize the rules and forget what they were supposed to mean. He wanted them to be able to stand in front of the double slit, or a sheet of glass, or a mirror, and think, even vaguely, somewhere behind what my eyes show me, there is a sum of possibilities, and the lines I draw in my notebook are only the residue of that sum. There is a quiet kind of humility embedded in this. The universe, seen through the path integral lens, does not behave in a way that flatters our instinct for single histories and clear choices. It does not act like an agent picking one route on a map. It acts like a system that allows everything the laws permit, but then, through interference, reveals only a thin subset of that, everything, in the form of outcomes. Once you admit that, the accusation that the path integral is crazy begins to lose its sting. Compared to the sheer weirdness of experiments like the double slit, the rule, add all the arrows, is almost conservative. It does not pretend to restore the world we were comfortable with before quantum mechanics. It simply organizes the discomfort into a calculable scheme. And so the feeling at the end of this idea is not one of having solved a mystery, but of having accepted a deeper one. If we can let go of the demand that light must honor our preference for one clean path, then the path integral ceases to look like a reckless indulgence. It becomes, instead, the only way of speaking that keeps faith with what the experiments have been shouting at us for more than a century. The universe tries every path it is allowed to try, not as a matter of intention, but as a matter of structure. What we see is the interference pattern drawn by that invisible crowd of possibilities, projected onto the fragile surface of our intuition. By now, the idea that light might somehow enlist every path it is allowed to take is no longer a punchline. It is a suspicion. The next step is to give that suspicion a shape your mind can actually hold, even if only loosely, on a quiet night. Feynman's favorite way to do that began with something almost childlike. He asked you to imagine that every photon carries a tiny clock. Not a clock with numbers or ticking sounds, just a hand that spins. The photon leaves the source. The hand begins to turn, and it keeps turning as the photon travels. When the photon reaches the detector, wherever that may be, the hand points in some particular direction on its little dial. That direction encodes what quantum theory calls the phase. Now forget the physical clock for a moment and look only at the hand. You can draw it as an arrow on a sheet of paper. The tail of the arrow sits at the origin. The tip points somewhere in the plane. That arrow is his picture for something more abstract. The amplitude. Amplitude is not probability. That distinction is the heart of why quantum interference is even possible. Probabilities must always add up in a straightforward way. If you flip a fair coin twice, the probability of getting heads on either flip is the sum of the individual probabilities. There is no room in that arithmetic for anything like cancellation. But amplitudes are different. They can be positive or negative, point east or west, spin around the circle. When you add amplitudes as arrows, they can reinforce or they can erase. The rule Feynman offers is brutally simple. For every possible path, from a starting point to an ending point, assign an arrow. The length of the arrow tells you how strong that path's contribution is. The angle of the arrow is set by the action along that path, translated through a factor that turns it into an angle on the unit circle. To find the total amplitude, you add all the arrows. Only at the very end do you take the square of the length of the resulting single arrow to get an actual probability. It is important to feel the order here. You do not square, then add. If you did that, you would be adding probabilities, and there would be no interference. You add first, as arrows, and then square. That single delay in squaring is where the strangeness lives. Think back to the two-slit experiment. In the old, bullet-like picture, you would say, the particle goes through the left slit, or the right slit. The chance of arriving at some point on the screen is just the sum of the chances of getting there from the left and getting there from the right. If that were the whole story, there would be no alternating bright and dark fringes. The pattern would be smooth, with perhaps a bit more light, where both beams overlap. In the arrow picture, the situation is more subtle. For a given arrival point on the screen, there are many paths that go through the left slit and reach that point, and many paths that go through the right slit and reach that point. You can group them into two broad families. For each family, you sum the arrows of its paths. Then you add the resulting two family arrows to get the total amplitude for that point. Only after that do you square to find the probability of seeing a photon land there. At some positions on the screen, the left family arrow and the right family arrow point roughly in the same direction. Their tips align, the resultant is long, and the squared length is large. Those are the bright fringes. At other positions, the left and right family arrows point in nearly opposite directions. They almost cancel, leaving a short resultant. Squared, that gives a small probability. Those are the dark bands, where hardly any photons arrive. Thomas Young, in his paper published in the Philosophical Transactions of the Royal Society in the early years of the 19th century, gave one of the first careful quantitative descriptions of this pattern. He spoke in the language of waves and path length differences, not in the language of arrows and action. But the shapes he described, the way the brightness swelled and faded across the screen, are exactly what Feynman's spinning arrows later reproduce. The mathematics under the metaphors is the same. The key lies in how the phase, the angle of each arrow, depends on the action. The action, in turn, depends on the route taken. Paths that differ only a little in their geometry tend to have actions that differ only a little. That means their arrows point in directions that differ only slightly. When you add a cluster of arrows that are almost aligned, they combine into a long arrow. Separately, small contributions become collectively loud. Paths that differ drastically, wandering off in wide loops or taking long detours, tend to accumulate actions that differ by large amounts. Their arrows arrive scattered around the circle, some pointing north, some south, some east, some west. Add a heap of such arrows, and they largely cancel. The tips spread in so many directions that the net result hugs close to the origin. This is where the traditional principle of least action re-enters the stage, but in a new guise. Historically, figures like Maupertuis, Euler, Lagrange, and Hamilton, across the 18th and early 19th centuries, noticed a curious thing. When you solve the equations of motion for a classical system, the path that emerges between two fixed endpoints is not just any path. It is a path that makes the action stationary. That is, if you make a small variation around that path, the first-order change in the action is zero. In many common situations, this stationarity takes the form of a minimum, which is why people often talk about least action. In the old, pre-quantum view, this principle was sometimes spoken of as if nature were a clever optimizer, comparing all possible routes and choosing the one with the lowest action, much as a thrift-minded traveler might choose the cheapest ticket. This way of speaking made some philosophers uneasy, because it seemed to sneak in a purposefulness, a sense of looking ahead into the laws of physics. Feynman's arrows remove that air of teleology. In the path integral view, nature does not need to choose. All paths are included in the sum. The stationary action path emerges not because it was preferred in advance, but because it is surrounded by paths whose arrows are roughly aligned. When you include the near neighbors in the sum, they do not cancel each other. They strengthen one another. Faraway paths, with wildly differing actions, send in arrows that point in so many directions that their net effect is nearly nothing. The classical path is, in that sense, a kind of ridgeline in the landscape of possible histories. Around that ridge, the phase contours are gentle, and contributions from nearby routes build a strong signal. Far from the ridge, the phase whirls so quickly with small changes in the path that any attempt to add contributions becomes an exercise in self-cancellation. If you like analogies that splash, you can picture a group of people standing around a calm lake, each holding a stone. Suppose they all agree on a spot near the center of the water where they want to maximize the height of the waves. If they coordinate, if they watch each other and time their throws so that all the stones hit the surface in rhythm, crest following crest, the waves can rise impressively high at that chosen point. Each person's contribution is small, but because the phases line up, the effects add. Now imagine the same group acting without coordination. Some throw early, some late, some weakly, some forcefully. In no particular pattern. The waves spread and meet, but crests collide with troughs as often as with crests. The water at the target point still moves, but the motion is modest, jittery, lacking any dramatic build-up. The same total energy has been expended in throwing stones, but because the phases are scrambled, there is little to show for it in any one place. The arrows in the path integral behave in something like this way. Paths with nearly the same action are like people who have agreed on a rhythm. Their phases are aligned or slowly varying, and so they have a chance to leave a visible mark. Wildly different paths are like uncoordinated throws. Their contributions are not forbidden. They are just self-erasing. This perspective also helps to correct a common misunderstanding. When people first hear that all paths contribute, they sometimes imagine a kind of democratic equality among histories, as if the path that hugs close to the classical route and the path that wanders to the edge of the galaxy and back before reaching the detector were somehow equally responsible for what we see. The truth is subtler. The theory does indeed assign an amplitude to every allowed path. In that sense, no path is excluded from the grand accounting. But the way those amplitudes combine is ruthless. The more a path diverges from the stationary action corridor, the more its phase tends to whip around relative to its neighbors. In the sum, its voice is drowned out by neighboring voices singing in conflicting keys. The classical path is not enforced from above. It is selected from below by the structure of the interference. This is why it is so powerful to carry around the image of the tiny spinning clock on each photon. When a photon leaves the source, you can imagine all those clocks starting together from the same orientation. As the various hypothetical paths wind their way through space and time, the clocks advance at rates set by the action densities along their routes. By the time they reach the detector, their hands point in a scatter of directions. Where the paths are similar enough that the actions agree to within a small margin, the hands point almost together. Where the paths differ wildly, they point everywhere. Add those hands as arrows, and you will see, in your mind if not on paper, which region of the path space is doing the visible work. At points on the screen where a bright fringe appears, the combined arrow from the left path family and the right path family is long. You can almost hear the clocks saying, in unison, "Here." The contributions were still counted. But the final sum whispers, "No." The same logic applies when light reflects from a mirror or refracts through a piece of glass. In the textbook picture, you draw a straight incoming ray, a straight outgoing ray, and construct equal angles. In the path integral picture, you imagine countless ways a photon might leave the source, graze this part of the mirror or that part, spend a little more time in the glass or a little less, and end up in your eye. Each option carries its own arrow. Where the action changes slowly with small shifts in the reflection point, the arrows align and the contribution is strong. That alignment picks out the familiar law that the angle of incidence equals the angle of reflection, not as an axiom, but as an emergent condition. When you move beyond single surfaces into complicated optical systems with many layers of material, the same rule applies. Anti-reflection coatings on lenses, for example, are designed so that the arrows associated with certain unwanted reflection paths cancel each other. Thin film interference, which produces the shifting colors on soap bubbles and oil slicks, is another case of phase engineering. The world you see is a tapestry of constructive and destructive interference patterns, sculpted by thicknesses, refractive indices, and geometries that control how the action accumulates. Historically, the seeds of this way of thinking were planted long before quantum mechanics. Maupertuis argued that nature chooses paths that minimize a certain quantity related to energy and time. Euler and Lagrange gave that idea a firm mathematical footing, turning it into a variational principle. Hamilton wove it into a canonical formalism that unified optics and mechanics in a surprising way. What none of them had, because the experiments had not yet forced the issue, was the notion that all non-stationary paths are still part of the story, not as rejected options, but as present contributions that happen to neutralize one another. Feynman's upgrade was to marry this older tradition of least action with the probabilistic, amplitude-based framework of quantum theory. Instead of one path chosen by minimizing action, you now have a weighted sum over all paths, with the stationary ones standing out because of how the weights interfere. The ancient language of least time or least effort gives way to a more austere language of phase coherence and cancellation. Once you see it that way, the weirdness of quantum mechanics shifts location. It is no longer solely in the double slit or the photoelectric effect, those isolated paradoxes ritualistically recited in popular accounts. It is in the very idea that to predict what will happen next, you must consider what could have happened in all the ways the laws permit, and then let them argue through interference about what will actually show up. By the time you reach the end of this construction, you have acquired a small set of images that, if you let them, can begin to replace the old straight-line intuition. You have the spinning clock on each path, ticking at a rate set by the action. You have the arrows they define, being added tip to tail into a resultant whose length squared gives you a probability. You have the picture of bright regions where arrows align and dark regions where they almost cancel. You have the understanding that the classical path is the one around which the action is stationary, not because nature likes short routes, but because nearby paths hug it closely enough to sing in phase. With those images, you can look again at a beam of light crossing a room, at the glare on a window, at the rainbow in a film of oil on a puddle, and know that behind each familiar effect, there is this quiet machinery of phases at work. You do not need to write down an integral over infinitely many paths every time you see a reflection. It is enough to know that such an integral exists, and that if you were to compute it, the straight ray your schoolbook gave you would fall out as the place where the tiny clocks stop fighting and start agreeing. The mathematics of quantum electrodynamics is deep and, at full strength, demanding. But the intuitions Feynman built around it are disarmingly compact, an arrow for each possibility. Add them, square the result, then, and only then, ask what the world will probably do. If you carry that little toolbox with you, a clock hand, an action, an interference pattern, you will find that a great deal of what once looked mystical about light becomes, if not tame, then at least coherent. The universe's insistence on trying every path becomes less an affront to common sense and more a reminder that our common sense was built for a much smaller, quieter game. Once you let the idea settle that light is quietly summing over every route it is allowed to take, the most ordinary objects in your house begin to look like conspirators. A bathroom mirror is no longer just a flat surface. It is a place where an invisible argument between paths has already finished by the time you glance at yourself. So here is a question that sounds almost naive, but cuts surprisingly deep. Why does light, when it reflects off a mirror, behave as if it has always chosen the path that takes the least possible time from the source to your eye? If you draw the situation, it looks straightforward. A lamp is somewhere in the room. Your eye is somewhere else. Between them hangs a mirror. You can trace many bent lines that leave the lamp, hit different points on the mirror, and then reach your eye. Most of those lines will give a path that is a little longer, or a lot longer, than the others. Yet the actual bright path that the ray diagram shows you, the one that geometry singles out with its clean, equal angles, turns out to correspond almost exactly to the route along which light would take the shortest time, given that it has to bounce once on the mirror. In classical optics, this is captured in a compact statement called Fermat's principle. It says, roughly, that the path taken by light between 2 points is the one that makes the travel time stationary, often minimal, sometimes just extremal. It is as if the universe has solved a constrained optimization problem in the blink of an eye. Out of infinitely many possible broken lines between lamp, mirror, and pupil, it has picked the one that gets there fastest. When the French mathematician Pierre de Fermat proposed this way of thinking in the middle of the 17th century, it was as much a philosophical bomb as a technical one. Some readers heard in it the echo of older ideas about nature acting with purpose, choosing routes to minimize effort or delay. If light always finds the quickest way, does that mean it somehow knows, in advance, all the routes it could take and compares them? Is there a hidden intention in every reflection? Others pushed back, preferring to see the principle as a compact summary of deeper mechanical laws. Later, when people tried to reformulate reflection and refraction in terms of forces acting on corpuscles of light, they worked hard to show that the least time path could be derived from those forces, not assumed as a kind of goal in itself. Still, the puzzle remained emotionally charged. Why does this simple variational principle work as well as it does? In a darkened room, that question does not feel abstract. Take a point source of light, a flat mirror, and your own eye. Imagine sliding the point on the mirror, where the ray is supposed to bounce. For some positions, the path from source to mirror to eye is long. For others, it is shorter. Plot the travel time as a function of where you hit the mirror, and you will find a smooth curve with a minimum. Right at that minimum is the point that also makes the angle of incidence equal to the angle of reflection. The ray that classical optics loves is sitting exactly where the time-cost function is flattest. Seen through the lens of Fermat's principle alone, this looks like evidence of a kind of foresight. Light knows what lies ahead and arranges its route to save time. Feynman's way of telling the story removes the drama, but replaces it with something more radical. In the path integral picture, light does not survey the landscape like a strategic general. It does not make a list of every possible zigzag between emitter and eye and then choose the best. It contributes along all of them. You are allowed, in the calculation, to imagine a photon leaving the source, striking the mirror at every imaginable point, wandering slightly above or below the nominal plane, even pausing in your nightmares to loop back and forth before proceeding. Each of those possibilities carries an arrow, a tiny clock hand whose angle is given by the action. As you slide the hypothetical reflection point along the mirror, the action associated with that bent path changes. For points near the classical reflection point, a small shift along the mirror only slightly changes the total time the light spends traveling. That means the phase, the angle of the arrow, only shifts a little, If you draw arrows corresponding to all those neighboring reflection points and add them, they tend to point in roughly the same direction. Their contributions reinforce. The resultant arrow is long, farther away from the classical reflection point. A small shift in where the path hits the mirror produces a much larger change in travel time. The phase begins to spin more rapidly as you move along. Arrows corresponding to nearby reflection points point in very different directions. When you add them, they tend to cancel. The resultant arrow is short, sometimes vanishingly so. In that view, the path of least time is not something light chooses because it is economical. It is simply the place in the space of all possibilities where the phases stop fighting and start agreeing. The classical law of reflection, angle in equals angle out, drops out of the sum as a side effect of destructive interference around it, not as a primary command. The same idea can be carried into thicker, more complicated pieces of matter. One of Feynman's favorite examples in his public lectures on quantum electrodynamics was not a perfect mirror, but a piece of glass. Imagine a thick glass plate in air. Shine light at it from one side. Part of the light reflects off the front surface. Part of it enters the glass, travels a little way, reflects off the back surface, and comes back out through the front. Some of it can even bounce back and forth inside, undergoing multiple internal reflections before eventually escaping in one direction or the other. In a classical ray picture, you draw a few arrows showing these possibilities. Assign each one a certain intensity based on Fresnel's equations, and compute that only a small fraction, on the order of a few percent, of the incident light comes back from each surface. The rest is transmitted. What Feynman did was to re-express that whole story in the language of arrows and paths. For every hypothetical scattering point inside the glass, for every bounce, you draw an amplitude arrow. You account for the extra time the light spends going into the glass and back out. You include the effect of the refractive index, which changes the speed of light inside the material and hence the rate at which the phase advances. You include the chance that the photon is reflected rather than transmitted each time it hits a boundary. Then you add paths that involve one reflection at the front surface, followed by an immediate return, carry one set of phases. Paths that go into the glass, travel to the back, reflect, and come back out, accumulate extra action because of the additional distance and the slower speed in the medium. Their arrows are rotated relative to the first set. Paths that rattle around inside the plate for several bounces pick up even more phase twists and often end up pointing in near-random directions. When you add all these arrows, you find that the contributions from long, multiply-reflected paths mostly cancel each other, just as wildly wiggling paths did in the empty space examples. The main surviving contributors are a small family of relatively simple roots. The final resultant arrow has a certain length, and the square of that length gives you the net reflection probability from the surface as a whole. That number comes out to only a few percent for many common kinds of glass, in exact agreement with what laboratory measurements had found long before. In his Auckland lectures, and in the slim book developed from them, Feynman delights in showing how this arrow game reproduces familiar quantities, like about 4% reflection from each uncoated surface, without ever invoking the traditional ray laws directly. It is the same physics, but seen from a different floor of the building. On the top floor, you have geometric optics and its neat rays. On a lower floor, you have wave optics and its interference patterns. In the basement, you have path integrals and their sums over histories. They all describe the same building, but they emphasize different load-bearing beams. Now, walk from that lecture hall back into your own life. Pick up a camera, or a pair of prescription glasses, or a modern phone. Look carefully at the front of the lens. You may notice that it is not perfectly reflective the way a bathroom mirror is. You can see your own eye faintly, but the main impression is of transparency. Sometimes, under the right light, you will see a faint colored sheen, a greenish tint, or a purplish one, sliding over the glass as you tilt it. That sheen is not a flaw. It is a signature of deliberate interference engineering. Lens makers learned that if they leave a simple glass surface exposed, that few percent of unwanted reflection at each interface adds up. In a complex lens system with many elements, those little reflections can create ghost images, reduce contrast, and throw away precious light. The solution is to deposit very thin layers of other materials on the glass, each with its own refractive index, thickness, and optical properties. Those layers are not random. They are chosen so that the reflections from their various boundaries interfere destructively for certain wavelengths of light. In essence, the arrows corresponding to the unwanted reflection paths are lined up so that they point against each other and cancel. The arrows corresponding to the forward-going, transmitted paths are lined up so that they support one another. To an everyday user, the result is just the lens looks clearer and photographs look better. Underneath that simplicity is a careful tuning of the path integral. You do not need to know the thickness of each layer or the exact recipe of the coatings to appreciate the conceptual leap. A modern anti-reflection coating is a human attempt to choreograph the very process that Feynman's arrows describe spontaneously. The engineers may work in the wave language of optical path lengths and interference minima, but the dance is the same. They are arranging possible histories of photons so that some histories cancel in the sum and others survive. It means that when you look through a high-quality pair of glasses, the transparency you take for granted is being negotiated in real time by a multitude of microscopic paths through and within the thin films on the surface. Many of those paths are being silenced by design. The clear view you enjoy is made from absence as much as from presence. Once you see that, the old story about light taking the path of least time becomes less reassuring and more subtle. In the mirror case, the least time route emerges because neighboring reflection points contribute phases that align. In the coated lens case, the favored path is shaped by layers that enforce destructive interference for certain directions and wavelengths. In both, what lasts is not the quickest journey in a naive sense, but the configuration of paths whose collective phase structure is most stable under the sum. Seen this way, Fermat's principle is not so much a sign of purpose in nature as a special case of a more general fact about wave and quantum systems. Stationary points in the action landscape are the places where contributions from nearby possibilities add up instead of wiping each other out. Calling that least time is convenient in simple isotropic materials. Beyond that simplicity, the language becomes richer. Least action, stationary phase, constructive interference. The photon, in this picture, does not peer into the future to see how long each road would take. It does not have a goal. It participates, impersonally, in a sum over all roads permitted by the laws. The ones that survive our gaze are precisely those where the phases have conspired to leave a clear imprint. There is a kind of comfort in this impersonality. The world does not need hidden intentions to produce the patterns we see. But there is also a quiet unease. If the rules that shape the path of a single ray on your bathroom mirror are the result of a huge, blind interference among possibilities, then many of the clean, straight lines in our mental picture of reality are just the last surviving threads of a much denser fabric. The next time you catch your reflection as you lean over the sink, you might pause a heartbeat longer. The little white streak of light that runs along the curve of the tap, the sharp glint on the edge of the faucet, the rectangle of brightness framing your face in the glass, all look like the work of single rays following obvious routes. Behind each of those rays, if Feynman is right, is a silent conference of paths that have already cancelled one another to make room for the one journey your eyes are allowed to notice. It would be comforting if this whole story about paths and arrows belonged only to light. We could tuck it away in a special drawer labeled "Photons are weird" and leave the rest of the world alone. What makes the ground move under your feet is that the same rules reach out, quietly, to everything built from matter. The first person to say this out loud, with full seriousness, was a young French prince of ideas named Louis de Broglie. In the year 1924, he wrote a thesis that sounded almost reckless at the time. If light, which had long been treated as a wave, sometimes behaves like a particle, why not flip the question? What if particles themselves carry waves? De Broglie proposed that every particle with momentum has an associated wavelength, not a visible ripple in space you could ever hope to see with your eyes, but a wavelength that shows up in the way the particle can interfere with itself. For an electron, that wavelength is small. For a neutron, smaller. For an atom or a molecule, smaller still. But small is not the same as non-existent. No one had seen such matter waves then. He was, in a sense, offering a dare to experimentalists. They took it. A few years later, two researchers, Clinton Davison and Lester Germer, found themselves with an electron gun, a nickel crystal, and a puzzle. They were studying how electrons bounced off the surface of the crystal, thinking in terms of impacts and scatterings, as you might. When they rotated the crystal and measured the intensity of the scattered electrons at different angles, they began to see peaks, bright directions where many electrons preferred to go, separated by angles where almost none arrived. The pattern was not random. It matched the same kind of diffraction pattern that X-rays, known to be waves, produced when passing through crystals. It was as if the regular arrangement of atoms in the nickel was acting as a three-dimensional diffraction grating for electron waves, steering them into certain directions by constructive interference and steering them away from others by destructive interference. Their results, published in the year 1927, were one of the first hard, undeniable stamps of approval on de Broglie's idea. Electrons were not just little bullets. Under the right conditions, their behavior was indistinguishable from that of waves. Once that door opened, other examples followed. Electrons sent through two slits form the same kind of interference pattern on a distant screen as light does. Narrow the beam until, once again, only one electron is in flight at a time, and you still see the pattern slowly grow dot by dot. Add detectors to learn which slit each electron went through, and the interference fringes dissolve into two broad humps. Turn the detectors off, and the fringes reappear. Every twist that light had already forced us to accept now replays with matter. Feynman liked to say that in some sense, all the mysteries of quantum mechanics are already wrapped up in that two-slit experiment. He did not mean it rhetorically. In his language of path integrals and arrows, the same set of rules that generates the photon pattern also generates the electron pattern. The only difference lies in the recipe for the action, the quantity that sets how fast each little clock hand turns as the particle travels. For a photon, the relevant pieces involve the properties of the electromagnetic field. For an electron, they involve mass, charge, and the way the electron couples to fields. But structurally, the instructions are the same. For every conceivable path connecting the source and the detector, assign an amplitude arrow based on the action along that path. Add all the arrows. Square the length of the result to get a probability. It does not stop with electrons. Neutrons, which carry no electric charge but do carry mass and a magnetic moment, can also be sent through interferometers. Their slow waves can be split and recombined using clever arrangements of crystals. When this is done carefully, the count rate in the detectors at the end shows the same rise and fall, the same dependence on phase shifts as any wave experiment with light. Atoms can be cooled and guided so gently that their wave character stretches out and becomes visible in the patterns they draw when passed through gratings. Entire molecules, complicated clusters of atoms, held together in fragile chemical structures, have been launched through double-slit-like setups and shown to produce interference fringes. Some of these molecules contain dozens of atoms, even on the order of 60 or more, arranged in shapes that on a table would look almost macroscopic. In each new case, nothing fundamentally new has to be added to the theory. The path integral story simply has to be told with a more complicated action, one that accounts for internal vibrations, rotations, and couplings. The syntax does not change. Only the nouns and adjectives plugged into that syntax become richer. That is the part that can make you feel very small. We are used to thinking of quantum strangeness as a property of microscopic things. Photons, electrons, little beads in a mental model. The rule of thumb we absorb from popular culture is that the weirdness lives down there, and up here, in the world of chairs and trees and people, everything has been smoothed out into classical normality. The experiments with large molecules begin to erode that comfort. They show that as long as you can isolate a system well enough from its surroundings, it will behave in line with the same all paths at once logic, no matter how many constituents it has. The quantum description does not suddenly vanish when you cross some magical threshold in size. It continues, quietly, until something else intervenes. That something else is not a hard border drawn in the sand, but a process that physicists have come to call decoherence. To get an interference pattern from electrons or neutrons or molecules, you must keep each participant's possible paths coherent. That is, the relative phases between paths must remain well defined. The little clock hands must keep their meaningful relationships long enough to reach the detector. If those phases are scrambled by interactions with the environment, the interference patterns wash out. The system still obeys quantum rules, but the observable consequences begin to look classical. Imagine again the lake with stones being thrown into it. When a small group of people coordinate their throws, standing apart from the crowd, their waves can build a beautiful, structured pattern. Now imagine the same patch of water under a heavy, chaotic rain. Drops fall everywhere, at all times. Waves crash into waves from all directions. Any fine pattern you might have created is quickly drowned in the noise. In the quantum version, the environment is that rain. Air molecules, stray photons, vibrations in the supporting apparatus. All these can act as extra degrees of freedom that the particle or molecule becomes entangled with. Information about which path was taken leaks out into the surroundings. The phases between different paths become inaccessible, spread out over too many degrees of freedom. When you then try to look only at the particle's position on a screen, the effective pattern is a wash of probabilities without visible fringes. Decoherence does not say that interference has stopped happening. It says that the interference has been smeared into places we are not measuring. It is still there in the full, enormous sum that includes every atom of the air, every photon of stray light, every tremor in the walls. But for practical purposes, when we restrict our attention to a small subset of variables, the neat, bright and dark bands we associate with quantum behavior have faded into a blur. From this angle, the boundary between the quantum and the classical is not a wall. It is a gradient of vulnerability. Small, isolated systems can keep their phases coherent over long times and distances. Larger, more connected systems decohere rapidly. A single electron in a well-designed vacuum chamber can maintain a kind of double life, exploring many paths at once, long enough to draw an interference pattern. A grain of dust in the same chamber is buffeted and illuminated in so many ways that any delicate phase relations between its possible paths are shredded almost instantly. Yet, in principle, the dust grain has a wave function just as surely as the electron does. And in principle, if the dust grain could be perfectly isolated, cooled, and shielded, it too would be describable as a sum over paths with meaningful interference. The path integral does not cut off at some particular mass or size. It simply becomes so hard to keep coherence for large things that our world, at human scales, very quickly looks like a place where only one path ever really matters. What Feynman's formulation whispers, if you listen closely, is that this feeling of one path only is not a fundamental truth, but an emergent approximation. It is a story that becomes good enough when the system you are talking about has been entangled so thoroughly with its environment that any competing histories have had their differences erased from the slice of reality you can. Observe, the unsettling consequence is that there is no clean place to stand outside of quantum behavior. The electrons in your nervous system, the protons and neutrons in your bones, the atoms in the air you are breathing, all belong to the same world as the electrons in a Davison-Germer setup, or the molecules weaving interference fringes in a lab. The difference is not that some obey path integrals and others do not. The difference is how long their fragile phase relations can survive immersion in the rest of the universe. You might be tempted to push back. Surely we, as conscious beings, are not just bundles of interfering amplitudes that have mostly decohered. Surely our choices, our memories, our sense of moving along a single storyline are made of something more solid than that. But the path integral does not care about our intuitions. It was built to be faithful to experiments. Those experiments, from the early days of electron diffraction in nickel crystals to modern interference with large molecules, have shown over and over that the same mathematical grammar can describe light, electrons, neutrons, atoms, and beyond. It scales outward as far as we can keep coherence intact. Where coherence vanishes, the grammar does not break. It simply hides its most poetic sentences from us. In a quietly ruthless way, the path integral picture says this: even we ourselves, made of electrons, protons, and neutrons, are the product of a universe that always, in its underlying description, sums over all the paths it is allowed. We live in the sharp, narrow narratives that survive that sum, the single lines in the mirror, while the vast majority of possible histories cancel one another in a calculation that goes on, indifferent to whether anyone is watching. Those narrow narratives that survive the sum over paths do not stay confined to blackboards and lab notebooks. We have frozen them into glass, etched them into silicon, and slipped them quietly into our pockets. If all of this had stayed at the level of abstract philosophy, we could safely ignore it on busy days. But every time you unlock your phone, watch a video, or send a message across an ocean, you are leaning on the same invisible arithmetic of paths that tells light how to get from a source to a screen. Take the laser. In ordinary light, like the glow of a bulb, photons are born in chaotic conditions. Each one is emitted at its own time, with its own phase, as if each carried a clock hand pointing in a random direction. When those arrows are added, the result is a kind of shimmering average. Bright enough, useful enough, but not disciplined. The phases do not line up for long, and the light spreads. A laser does something more focused. Inside a cavity lined with mirrors, a material is pushed into a strange state where many atoms are ready, under the right nudge, to drop from a higher energy level to a lower one and emit a photon. When a photon already traveling through the cavity passes by such an atom, it can stimulate the atom to emit another photon that is almost perfectly in step with it. Same frequency, same direction, same phase. Each new photon is born with its little clock hand aligned to the one that came before. Once this process gets going, the cavity fills not with a noisy mixture of possibilities, but with a marching band of photons whose arrows all point nearly the same way. When the light leaks out through a partially reflecting mirror at one end, what emerges is a beam with an exceptionally well-defined phase and direction. In the language of path integrals, the contributions from many possible paths are not just allowed to add, they are herded into coherence. The sum over paths becomes highly organized. On May 16, 1960, at Hughes Research Laboratories in Malibu, Theodore Feynman turned on a device built around a synthetic ruby crystal and watched it emit a pulse of this new, unnervingly precise light. It was the first working laser. The first time humans had persuaded matter to produce such a disciplined sum of photon paths on command. The beam was not very powerful by later standards, but it was conceptually radical, a macroscopic, visible demonstration of phase control. From that moment, lasers slipped into almost everything. Send information down an optical fiber across a continent, and you are relying on a laser whose photons have been launched into a glass thread so thin you could barely see it, bouncing internally along carefully controlled paths. Tiny variations in the phase, intensity, or polarization of that coherent beam are used to encode data. The path integral does not change to honor our communications protocols. We design our protocols around what the sum over paths will naturally preserve and what it will happily scramble. Read data from a compact disc or a digital video disc, and a laser picks out pits and lands as it sweeps over a surface. The difference in reflection from those microscopic structures, controlled by interference at the scale of the wavelength of light, is translated into ones and zeros in the device's own language, then into music or images in ours. Medical devices, from simple barcode scanners to sophisticated surgical systems, use focused laser beams, relying on their tight path coherence to cut cleanly, measure precisely, or illuminate selectively. Even the apparently soft act of measuring distance to the moon uses this discipline. Laser pulses sent from Earth, reflected by retroreflectors left on the lunar surface, return after a journey of about a few seconds. The timing of their arrival can be measured with such accuracy that the path length differences corresponding to millimeter changes in the distance become detectable. Underneath those numbers is the same picture: light exploring all allowed paths between emitter, reflector, and detector, with the least action route emerging as the ridge of constructive interference. Meanwhile, under the surface of your phone or laptop, an entirely different kind of quantum device is doing its own quiet work. Transistors and integrated circuits are often drawn as simple symbols on circuit diagrams, treated as idealized switches or amplifiers. At that level, engineers talk in a language that sounds comfortably classical: voltages, currents, resistances. But the behavior that makes a transistor possible in the first place, electrons living in energy bands, forbidden gaps where no electron may sit, tunneling through barriers that would stop a classical particle cold, is rooted in the same quantum rules we have been tracing. In a pure, infinite crystal, electrons arrange themselves in allowed and forbidden energy bands because their wave functions must satisfy certain boundary conditions and symmetries. In a small, patterned slice of semiconductor, these bands can be manipulated by adding impurities, layering materials, and shaping potentials so that electrons are encouraged to flow one way under certain conditions and discouraged under others. The probability that an electron will pass through a narrow barrier instead of reflecting from it is not guessed. It is computed from amplitudes, integrals over paths through the barrier region, each path weighted by its action. In the late 1940s, when the first point contact transistors were built, the designers did not talk in terms of path integrals. They leaned on an earlier formulation of quantum mechanics, using wave functions and band diagrams. Yet, the underlying agreement between theory and experiment that allowed them to trust those diagrams came from the same place: a quantum theory of matter that had already proven itself in scattering experiments, spectral lines, and the behavior of electrons in solids. By 1956, when John Bardeen, Walter Brattain, and William Shockley were honored with the Nobel Prize in Physics for the invention of the transistor, a new age of electronics was underway. It would lead, via integrated circuits and microprocessors, to the devices on which you might be reading these words. Without quantum mechanics, without the notion that electrons in solids must be described by overlapping amplitudes and energy bands, there would be no transistors to turn on and off in ordered cascades of logic. Look down, now, at an organic light-emitting diode screen. Behind the smooth grid of color, each pixel is a tiny theater of quantum events. Organic molecules sandwiched between electrodes are being pushed into excited states by electrical currents. Electrons and holes, formal names for missing electrons behaving like positive particles, meet and recombine. When they do, they release energy as photons. The color of each photon depends on the energy gap between the states involved. That gap is a property of the molecular structure, itself fixed by the quantum mechanical arrangement of electrons around nuclei. Each emitted photon is a kind of punctuation mark at the end of a path integral story. There were many ways the electron and hole could have moved, interacted, scattered, and finally met. There were many ways the photon could leave the material, bounce internally, emerge from the surface. All of those ways, in principle, are part of the sum. What you actually see when you look at your screen is the thin residue of that vast internal accounting. A patch of blue or red or white, small squares of certainty emerging from oceans of possibility. When you press a virtual button on the screen, you are setting in motion countless such stories. Electron paths in the circuitry beneath your fingers. Photon paths in the layers of emissive material. The network of paths in the fiber beyond your device. Each step is, at its base, a manipulation of interference, a leveraging of the fact that quantum systems will respond differently when phases are aligned or scrambled. This is why the path integral is not a luxury. It may sound like a mental game played by theorists late at night, but its consequences are written into the light on your walls and the hum of your machines. Every time a laser pointer draws a red dot on a presentation slide, paths are being disciplined. Every time a chip switches state, amplitudes are being guided through carefully engineered landscapes of action. If you let this sink in, the cheap laser pointer on a keychain stops being just a gimmick. It becomes a small, handheld orchestra in which an entire ensemble of possible photon paths has been forced into almost perfect unison. You press a button, and a tiny volume of matter, shaped by quantum rules, performs a piece that the universe will always approve of, because it never violates the grammar of its path sums. We live, without quite admitting it, in a civilization that has learned to steer sums over invisible paths, and has given that art a plain name: technology. When you realize that our devices are already steering quantum paths for us, the questions stop being about lasers and screens and start circling back, quietly, to us. If the same mathematics that routes a photon through fiber also underlies every atom in your brain, what does it really mean to say that anything chooses a path at all? We say it all the time, without thinking. We ask which route the light took through the two slits. We say a photon decided to reflect or transmit at a piece of glass. We talk about an electron choosing a particular orbit or a particular outcome. The verbs are borrowed from human life. Decide, choose, prefer. They smuggle will into places where there is no nervous system, no memory, no self. In Feynman's language, that is not what is going on. The path integral does not describe psychological decisions. It does not picture a photon arriving at a fork and pondering its options. It says something colder and more general. For every allowed path connecting a starting event and an ending event, the universe assigns an amplitude, a complex arrow whose angle is fixed by the action along that path. Then the universe, through the arithmetic we have learned to write down, lets those arrows add. Where they reinforce, you get a high probability of a detection. Where they cancel, you get almost none. There is no little committee inside the photon voting on routes. There is only a rule that turns possibilities into numbers and then into frequencies of observed outcomes. When we say the light chose that path, we are not describing an inner process in nature. We are naming the single visible thread that remains after countless alternatives have quietly annihilated each other in the sum. This is where the word reality starts to wobble. Is reality the whole collection of paths with their associated amplitudes, a vast, shimmering set of almost histories, most of which never show up as actual records? Or is reality only the final pattern on the screen, the definite clicks in the detector, the particular reflection you see in the mirror tonight? The path integral by itself does not answer that. It gives you a recipe for predicting the pattern of clicks. How you promote that recipe into a picture of what exists is where interpretations begin. The Copenhagen-style answer, shaped by Niels Bohr and his circle, is cautious. The wave function and the path integral are tools for computing probabilities of measurement outcomes. Nothing more, asking which path was real before the measurement. In that view, is asking a question the theory is not built to answer. The world is what we can say about it, not what we imagine might have happened behind the scenes. Other voices, later grouped under names like many worlds, suggest a bolder story. Perhaps all paths, in some sense, do occur, each in its own branch of a larger, multiplying reality. And what we call the outcome is simply the branch we happen to occupy. In that view, the path integral is not just a calculator, but a census of real, parallel histories. The path integral itself is neutral. It does the same job for both philosophies. It encodes in one compact expression the way amplitudes from all possible routes combine. It is we who ask the extra question. Are those routes merely terms in an equation, or are they ghostly but real strands in a thicker fabric of the world? Long before Feynman, this tension between chance and reality haunted the early quantum theorists. In the years between roughly 1920 and 1930, Einstein and Bohr argued about it in a series of meetings that later generations gathered under the name of the Solvay Conferences. Einstein, who had helped launch quantum theory with his work on light quanta, was deeply uncomfortable with the idea that randomness was baked into the deepest level of physics. He summed up his unease with a line that became famous: "He did not believe that God plays dice." Bohr, for his part, thought that Einstein was holding on to an image of reality that the experiments had already outgrown. If the only theories that survived careful testing were theories that made intrinsically probabilistic predictions, then perhaps that was simply how the universe worked. Probability was not a confession of ignorance. It was a basic feature of the world. From one angle, the path integral is the clearest statement imaginable of the dice being thrown. You do not have a single random event, a coin toss here or there. You have a random structure built into the contributions along every possible path. The amplitudes are not themselves random. They are fixed by the action. But when you square the total and ask what will happen this time, you get only a distribution of chances, not a fixed edict. That is what the dice metaphor was always trying to get at. Later, philosophers like Karl Popper would emphasize falsifiability as a standard for scientific theories. A good theory, in that view, is one that makes definite predictions which could turn out to be wrong. If the predictions survive many attempts at refutation, the theory earns our provisional trust. Quantum mechanics, whether written in the Schrödinger form or in Feynman's path integrals, does exactly that. It gives you precise probabilities for interference patterns, spectral lines, scattering cross-sections, device behaviors. Those probabilities have been checked against experiments so many times that counting them is no longer meaningful. From the first electron diffraction experiments to the fine structure of atomic spectra, from the stability of solids to the behavior of transistors, the quantum rules have passed every test we have been able to devise. Meanwhile, many more intuitive alternatives, theories that try to restore a simple, deterministic picture under the surface, have stumbled when confronted with the data. One turning point in that story came with the exploration of Bell's inequalities. In the second half of the 20th century, John Bell showed that any theory that tries to keep both locality and pre-existing hidden values for measurement outcomes must satisfy certain mathematical inequalities. Quantum mechanics predicts violations of those inequalities in specific experimental setups involving pairs of entangled particles. When those experiments were carried out, with increasing care and sophistication, the violations were observed. The world does not behave as if each particle carried a fixed, private list of answers written in advance, unaffected by what happens far away. Path integrals, again, do not care about our shock. They simply encode the same quantum correlations in their own language. When you include in your sum all the joint paths of two particles that have interacted and flown apart, the resulting amplitudes reflect a non-classical linkage between their outcomes. You can draw the diagrams, compute the arrows, and find that the predictions match what the Bell tests see. A universe in which the connections between measurements cannot be explained by local hidden stories. So we arrive at an uncomfortable but stable place. We have a framework that predicts, with uncanny success, how often different outcomes will happen, and that framework seems to insist on chance and non-local correlations at a fundamental level. Yet we still talk about particles choosing paths, as if there was some tiny deliberation going on underneath. It is not surprising, then, that the mind turns this back on itself. If, for a photon, choosing a path is just a convenient metaphor for interference between amplitudes, what about us? When you stand at a fork in your own life, a job you may or may not take, a message you may or may not send, are you making a genuine choice? Or are you simply the macroscopic, classical-looking branch of some much larger quantum process, the ridgeline emerging where other possibilities have decohered away? If you take the metaphor seriously, you might imagine your life as a kind of path integral over decisions and circumstances. At each moment, there are many ways things could go. Conversations you never start. Cities you never move to. Apologies you never deliver. Most of those possibilities, under the pressure of the world, cancel out. You follow one thread. Years later, looking back, you draw a straight line through the key points and call that your story. It feels like the only path you could have taken. But somewhere in the structure of all that could have happened, do those ghost paths still matter? Physics, at least in its current form, does not answer questions about free will in a satisfying way. Quantum indeterminacy is not the same as freedom, and determinism is not the same as meaninglessness. The path integral gives you a way to compute how likely it is that a system will go from one state to another. It does not tell you whether the feeling of having chosen among options is an illusion or a reflection of some deeper agency. Feynman himself was suspicious of grand metaphysical conclusions. Over and over, in his lectures and writing, he returned to a kind of disciplined humility. This is what the equations say. This is what the experiments report. Beyond that, he would say, we do not know. To pretend otherwise is to confuse our urge for closure with knowledge. There is a quiet wisdom in that stance. We have, in the path integral, a tool that tells us how light and matter behave in astonishing detail. It is tempting to elevate that tool into a total philosophy of existence, to declare that because the universe sums over paths, human choice is an illusion, or that because probabilities are fundamental, everything is absurd. But the data do not force those steps. They only force us to admit that the world is less like a clockwork and more like a web of weighted possibilities than our ancestors imagined. Maybe the most honest place to stand is here, accepting that we live in a universe where, at some level, every allowed path leaves a trace in the calculation, and yet we only ever inhabit one visible thread. What that means for responsibility, for meaning, for how we live, is not dictated by the equations. It is left, unavoidably, to us. In the world of path integrals, the sentence, "light chooses a path," is only a metaphor. But it is a metaphor that helps us talk about ourselves, about how each choice we call our own may be the single bright remnant of countless possibilities that never came to be. Once you start to feel that every outcome is the last surviving thread of many cancelled possibilities, it becomes strangely difficult to stand at a real crossroads in your own life and believe you are only choosing between two clean lines on a map. Picture someone alone at night, standing in the kitchen or on a balcony, staring past their own reflection in the glass. A job offer sits in their inbox. A message, half-written, waits on their phone. A relationship is balanced on the quiet edge between staying and leaving. From inside their own head, it feels brutally simple. There is only one road forward. Say yes or no. Go or stay. Press send or delete. Light switches off in one room and on in another. From the point of view of experience, that is how it has to feel. We are built to inhabit one thread at a time. But if you carry the path integral in the back of your mind, even as a metaphor, the scene looks denser. Around that person, in the space of what could happen next, there is not one path, but many. There is the version where they answer the email at once, the version where they postpone it until morning, the version where they rewrite it, the version where they never respond at all. There are the accidental encounters that would follow one choice and never the other, the friendships that would form and the ones that would slowly evaporate. Each is like a little arrow that has not yet been added to the total. In physics, we do not say that all of those possibilities are real in the same way as the one that finally plays out. That would be an interpretive leap, not a forced conclusion. What we say, more modestly and more painfully, is that to compute the probability of what we actually see, we must respect all of the ways the world could have gone under the laws we know. Every allowed path gets an amplitude. Only after we have added them and squared the result are we allowed to talk about the outcome. There is something quietly ethical in that rule. It does not let us erase possibilities just because they make the calculation harder or our picture messier. The path integral insists that even the paths that cancel, the ones that never become part of any visible history, must be counted before they are allowed to disappear. When you turn that insistence back on your own life, it becomes harder to talk about the road not taken as if it were a simple ghost, a thin line parallel to the one you are on. In the light of the path integral picture, each unrealized road is not a single trajectory, but a sprawling family of could-have-beens, most of which would have cancelled one another long before they reached any clean narrative. The fact that you are here, now, reading this sentence, does not mean that all other futures were trivial. It means that, through a long chain of interactions and decoherences, this thread became stable enough to be lived. That sounds deterministic on some days and terrifyingly open on others. What it is, above all, is humbling. If we learn anything from Feynman's way of writing physics, it is that the universe does not organize itself around our intuitions. The straight lines we draw, the single paths we like to imagine, are conveniences, not laws. Light does not honor the childhood picture of a ray. Electrons do not honor the hope that they carry definite answers to every question before we ask. Even the principle of least time, which sounds almost moral when we first learn it, turns out to be the shadow of a deeper requirement, that nearby paths interfere in a way that leaves something coherent behind. From that perspective, regret looks a little different. When we say, "I should have taken the other path," we are imagining a world in which there was exactly one alternative road, clean and complete, waiting for us. In reality, that other road would also have been a tangle of probabilities and constraints, a place where countless potential histories would have been offered and then erased. The life you did not live would not have been a smooth movie. It would have been another interference pattern. That does not mean regret is meaningless. It means that, like the picture of a ray of light, it is a compressed summary of something much richer. You can still feel the weight of what you did and did not do, the harm you caused or avoided, the kindness you gave or withheld, but you no longer have to imagine that there was a simple, clean, guaranteed better line that you failed to spot on the cosmic map. Feynman's attitude, which shows through even when he is at his most technical, is one of pragmatic courage. Quantum electrodynamics, the theory in which his path integrals found one of their most precise forms, makes predictions that have been checked against experiment to an almost absurd degree. The magnetic moment of the electron, for example, can be computed in that framework and measured in the laboratory. The two numbers agree to many, many decimal places. The tiny difference between calculation and observation is smaller than almost anything else we have ever tried to predict. To reach that agreement, physicists had to do something that, at first, felt as reckless as allowing light to try every path. They had to accept that the mathematics would draw loops and squiggles, virtual processes, that never appear as classical events, and then insist on summing their contributions. They had to trust a method that, step by step, looked more and more alien to everyday reasoning, precisely because experiments kept confirming its outputs. There is a lesson hidden there for how we live with uncertainty outside the lab. We may never have equations for our own choices that are as sharp as the ones for electrons, but we can borrow the stance. Instead of clinging to the demand that the world be simple, that every event must fit into a story we already approve of, we can practice a softer kind of bravery, accepting that parts of reality will remain beyond what we can picture, and going on anyway, careful and curious. From that stance, the path integral stops feeling like a surreal party trick and starts to feel like a training ground in humility. It tells us, in a precise way, that the world is stranger than classical common sense, and that the strangeness is not a temporary fog that will lift as we learn more. It is structural. The fact that the same formalism can produce predictions as sharp as those of quantum electrodynamics is not a sign that we have tamed the strangeness. It is a sign that we have learned to cooperate with it. If you extend that spirit beyond physics, the effect is disarming. Look at history, for instance. We often talk as if there were inevitable paths, the inevitable rise of this empire, the inevitable fall of that system, the inevitable march of some technology. But when you look closely at the contingencies, the near misses, the accidents, it becomes clear that there were many ways things could have gone. The world we inhabit is only one realization out of a vast space of possibilities, most of which cancelled long before they touched us. Honoring that does not mean sinking into fatalism. It means being slower to declare that our preferred road is the only rational one, and gentler with those who see different paths through the same landscape. If the universe itself, at its most fundamental level, is constantly summing over many histories to produce a single visible pattern. Perhaps we should be wary of any politics, any ideology, any personal conviction that insists there is exactly one line through the future that deserves to exist. In the end, though, all of this cosmology and philosophy has to come back to something small enough to fit in a room. So imagine, one last time, a darkened space. The walls are quiet. The door is closed. On a table sits a lamp with a simple shade. When you switch it on, a pool of light appears, a circle on the table, the gentle gradient of brightness on the open pages of a book, the warm outline of a face leaning into view. To the eye, it feels intimate, contained. A bulb, a table, a person, a patch of illumination. But if you allow the path integral picture to overlay that scene, silently, the stillness becomes crowded. Each photon that finally lands on the paper, or on skin, has been part of a sum over countless routes through the room. Some brushed the edge of the shade and scattered. Some grazed the wall and turned. Some passed through the glass, through the air, through the slight shimmer of rising heat. Most of the hypothetical paths that could have linked filament and page have cancelled out in phase. What you see, the small, reliable circle of light on the table, is the surviving pattern, the classical path made manifest. You do not need to calculate any of that. Standing there in your socks, it is enough to know, in some corner of your mind, that the simple act of being able to see the words on a page is the endpoint of an unimaginably rich coordination among possibilities you will never witness. The universe has, in a sense, tried every path it is allowed. And this is what arrived. Maybe our lives are not so different. We feel the limits of only one way forward because we can only live on one thread at a time. Yet, around any decision, there is an invisible architecture of could-have-beens that shapes what is likely, what is even thinkable. We do not control that architecture, but we do inhabit one of its ridges, one of its relatively stable paths, and we can move along it with a little more honesty if we remember that it is not the only one the laws would have allowed. If light can explore every allowed route and still, somehow, find its way into a small room to illuminate a corner of a table, a book, a face, then perhaps we do not need to panic in front of our own branching futures. Between all the lives we might have lived, all the words we might have said or swallowed, there will be, at the end, one path that becomes the path we walked. Whatever else might have been, that is where we are real, and that, quietly, is enough.